Hello guys, welcome to Self Help Maths Academy. Today I'm going to talk about the subspace of the vector space. Let us understand what is the subspace of Rn. Okay, so in order to understand what is the subspace of Rn, it has to be first. Let us consider that in order to understand the subspace, as we know that this will be the Rn space. Okay, and here let this V is a subset, or if you want to take this V as a vector space, and then now let me take this as some S, which is the subset, okay, of this the whole vector space Rn. Okay, now in order to understand this S as a subspace of Rn, okay, then first condition is this is, yeah, obviously the first condition is it has to be a subset of the whole vector space. Now this this subset, yes, this subset, yes, must contain the zero vector. The first condition is this yes contains zero vectors. So when I say zero vectors, let me denote it as, say, something like this: zero vectors is equal to 0, 0, 0, 0, and say to n, as it contains all the n-dimensional elements. Okay, so now the first condition is what? It contains the zero vector. Second condition is, if I take the vector, say, x in, yes, there is some vector, say, x, which is coming from this subset, yes, then if I multiply that with any scalar, say c, then this must also should belongs to this S. So if x is belongs to this subset S, then after multiplying with the scalar, any scalar c, it must belongs to the same subset. It is nothing but in a very like formal term, we say that it is closed under scalar multiplication. It is closed under scalar multiplication. Okay, that is important. Now the third condition is, suppose I have a vector, say, y, or you can take y in S, and the vector, say, z in S. Okay, then the y, vector y plus vector z, this resultant vector also should be in S. So if I take the vector any vector, say, y, any vector, say, z, after adding these two vectors, the resultant vector must also belongs to here. It cannot come somewhere here. It cannot come somewhere here. Same way, when you take a scalar multiplication, it should belong to this collection only. It cannot come outside this collection. All right. So in again the formal way of saying this is nothing but closure under close under the addition. Close under addition. Okay, so if that is happening, if these three conditions are satisfied, then we say that this subset S of the vector space Rn will become a subspace. This will become a subspace. I think let us understand this particular result or the definition with the help of example. So now let me consider the example. I have a set, say S, which is just containing the zero vector. It contains the zero vector. More specifically, if I have to write, it is, say, the zero vector in R3. Okay, let me consider this. It contains a zero vector in R3. The question is this yes is a subspace is it a subspace of R3? Is it a subspace of R3? Let us understand this. Now, as we know that since it is zero vector, since this is a zero vector, so the first condition for a subspace is the zero vector, it should contain a zero vector. So this itself is a zero vector, so therefore it contains the zero vector. So therefore there is no issue of finding the zero vector here. It contains the zero vector. Okay, zero vector is there. Now the second condition is whether it is closed under the scalar multiplication. Let us see. Now I'll take an element of this particular collection, as we have only one vector here, so that's 0 itself. So this 0, 0, 0 vector, if I multiply with any scalar c, obviously the resultant vector is what? 0 times of c, 0 times of c, 0 times of c, it is 0, 0, 0 vector. So this 0, 0 vector still belongs to this collection. That means what? It is closed under the scalar multiplication. The second property holds true. The third property is, now take any two elements of the collection of this vectors. Obviously there is only one availability. So let me take that set its so the 0, 0, 0 I'm taking with 0, 0, 0, 0. If you add it, so it is simply what? 0, 0, 0. So if you observe carefully, if I add the vectors which belongs to this collection, it gives me the 0 vector itself. Still it belongs to the collection, right? So this is closed under addition. Therefore 0 vector is belonging, the scalar multiplication is closed, and addition of it is closed under addition as well. So therefore this collection will form a subspace of R3. Okay, so this is one example. Now let us understand another example. So let me take another example. Let me define it as some v equal to, or let me take it as, say, some p equal to. Okay, so this is x1, x2. Okay, this is belongs to R2. It is in 2 dimension, and the condition will be, the constraint on x1 will be, say, x1 is greater than or equal to 0. Okay, so here we have the collection of x1 and x2 in such a way that it should be what? It should be the condition on x1 should be greater than or equal to 0. So in the geometrical meaning, let us try to see it how it actually goes. So they have given you P, which is x1, x2, and x2, which is belongs to R2, such that your x1 is greater than or equal to 0. All right. So now if you observe this x1 greater than or equal to 0 means, suppose if I just try to draw here, it looks something like this. So this is your 0, say 1, 2, and so on, -1, -2. So all this are this is your x and this is your y. So if you observe, in particularly here I'm taking this as x1 and this as, say, x2. So here x1 is greater than or equal to 0 means it is taking this all the values, right? So these are my x1 values, because strictly it has to be greater than or equal to 0. But there is no condition on x2, so x2 may take this values, or it may, the positive values, or it may also take the negative values. So that means we are having the coverage of all the first and the fourth quadrant. So that's how it actually looks like. Okay, these vectors actually they fall in here. That is the understanding geometrically. Okay, so is it a subspace of R2? That is the question. Now when we check it like geometrically, if you observe carefully, as it contains all the points, okay, so these all the points it contains, so it also includes what? The point 0, 0. So that means this 0, 0, the 0 vector, the 0, 0 which we were talking about, the 0, 0 which belongs to R2. Obviously this is greater than or equal to 0. The condition on this has to be greater than or equal to 0. It's obeying. The remaining is the remaining value, it may take anything because there is no restriction on x2. But when it actually take x2 as 0, so it obeys that it contains the 0 vector. Okay, so therefore 0 0 belongs to R2. So you can see that this also is a part of your the P, the set of P. Okay, how you define. So 0 0 belongs to R2. That is our first condition. The second condition, the first condition is obeying. The second condition is, let us check whether the it contains the scalar multiplication, whether it is closed under the scalar multiplication. So for that, what we do, let us consider the let us consider that the two vectors, whether we are checking with whether this is having the, whether it is closed under the scalar multiplication or not. For that, what I do, let me take the vector, say x and y, or any vector, because x and y, in the sense, don't worry, this x is nothing but this x1, y is nothing but this x2. Okay, I'm just taking it in that form. So this is my vector which obeys this condition, okay, the given condition. Let me take a scalar as, say, -1. Okay, so if I take a scalar as -1, so this gives you what? This gives you -x, -y. Okay, obviously there is no condition or the restriction on y, but it has to be strictly positive, right? So therefore you can see that this minus x, this is not greater than or equal to 0, hence it fails. Therefore it is not closed under scalar multiplication. It is not closed under scalar multiplication. Obviously this is enough for us to say that it is not a subspace. But sometimes if you check that say 0 vector belongs to, also, in this case even addition also actually follows. For example, if I take a vector like say a and b, this is my vector, and say I'll take b and c and d. Let me take another vector as c and d. Okay, so if I take the addition of these two vectors, okay, so if I add these two vectors, if it follows like a plus c and b plus d. If you observe carefully, as this is greater than 0, this is greater than 0, so the sum also should be what? It should be greater than or equal to 0. It's a non-negative, right? These are the non-negative, so therefore addition will be non-negative. And as we don't have any restrictions on b and d, so nothing to worry about here. It still belongs to the collection P. That means it is closed under addition, but it fails to be having the not it fails to be having the closed under the scalar multiplication. Therefore what we can say, this collection P will not be a subspace. It is not a subspace. It is not a subspace of R2. Okay, so that is another understanding. Now let us consider the another example. So if I take, say, span of the vector v1, v2, v3, okay, is it a valid subspace of R3? That is the question. Is it a valid subspace of R3? So to understand that, that what is the span of the vector? Span of the vector is the list of all possible collection of linear combination of these vectors, right? So therefore, when I take a list of all possible collection of linear vectors, so as when I say this list of possible linear combination, so I'm talking about this, so set of all possible linear combination. So we also may have the set of all linear combinations where C1, C2, C3 all are 0. If all are 0, so then we'll have this combination 0 into V1, 0 into V2, 0 into V3, which is nothing but what? A 0 vector. So this is also one of the possible combination in this span of the vector. So therefore the first property, that 0 vector belongs to, the first property says that we have to check whether the 0 vector belongs to this collection. So yes, the 0 vector belongs to this collection because this is also one of the linear combination. Now to check the scalar multiplication, the second one, to check the scalar multiplication, let us consider the vector y, okay, say as c1 v1, c2 v2, and C3 V3. Okay, so let us have this vector. Now what we do, this the vector y is C1 V1 C2 V2 C3 V3. In order to check that it is obeying the scalar multiplication, let me take a scalar, say k times of y. So I'm multiplying the whole vector by y, so therefore let me multiply it on the right hand side as well. So it is simply k into C1 times of V1, k into C2 times of V2, and k into C3 times of V3. So if you observe carefully, so this is basically the scalar. This is a scalar, this is a scalar. So we can just take it this as some new scalar, say a1, or if you take it as, like, say maybe the new scalar, say c4, c5, and say c6. So we will get what? We will get c4 times of v1, c5 times of v2, and c6 times of v3. So this is nothing but again a linear combination, another possible linear combination. So this is still belongs to where? The span of the given collection. So therefore the scale, it is closed under the scalar multiplication. It is closed under the scalar multiplication. Okay, scalar multiplication. All right, and then whether is it also closed under the addition, that's what we have to check. Now consider, let me take this as the vector y. Let me take another vector, say z is equal to some d1 v1, say d2 v2, and say d3 v3. Okay, so we have got a vector y, we have got a vector z. So let me add now vector y with vector z. So this will be c1 plus d1 times of v1, and c2 plus d2 times of v2, and c3 plus d3 times of v3. Okay, so this is the new resultant vectors. If you see, c1 plus d1 is again, it will give you a new scalar, this will give you a new scalar, this will give you a new scalar. So therefore you will be having a resultant what? A new scalar with a new combination. So this will be nothing but it is closed under addition. So this is nothing but it is closed under addition. Okay, so it is closed under addition. So hence what we can say that span of this collection will become a subspace of R3. Okay, so now let us see, is it generalized? We can generalize this particular thing, or is it possible to generalize that span of any collection will become a subspace, or it is like how? That's what we have to see now. So to check that, now let me take another vector, say u, which is equal to span of say 1 1 I have. Okay, so this is there is a collection which contains span of this vector. Okay, so the set of all linear combination of this vector we have. So when I say this is 1 1, so geometrically if I just draw it, it looks like this. So if x is say 1, y is say 1, okay, like this. If you just take the linear combination of this, it will be like this line when you take a positive and when you take a negative. So this is this line on which we'll be talking about. Okay, so this is this line. All right, so now let us see whether the zero vector will be a part of it. So as I said, when I take a scalar as 0, okay, if I take a scalar, because it's a linear combination of this vector, when I take my scalar as 0, okay, and I multiply this vector with 1 and 1, I'll be getting what? I'll be getting a 0 0 vector. So that means this 0 0 vector is a part of this collection, which also lies on this line. If you see geometrically, it lies here. So therefore 0 0 vector belongs to the set U, where U is nothing but what? It's a span of the vectors 1 comma 1. So therefore the first property, it holds. Okay, and then the second property is about the scalar multiplication. So whether it is closed under the scalar multiplication or not. So if I multiply any scalar, say C, to the vector say 1 comma 1, okay, so if you observe carefully, so if I multiply this with 1 comma say 2, so it will become 2 comma 2 with 2. So this is here. Okay, this is here. When I multiply with say negative 3, somewhere here. So when I multiply with 4, somewhere here. So it actually, as long as it is on this same line, okay, so that this is nothing but what it is it is any linear combination will be lying on the same line. All right, so therefore you take any scalar here, when you multiply with the given vector, so this is still belongs to the set U. So therefore it is closed, it is closed under multiplication, it is closed under multiplication. Okay, now let me take the third one. So if I add two vectors, so as we know that it is all the formation of that. For example, let me take with the a 1 1, so this is my scalar. Let me take another scalar as b with the 1 1. Okay, so let us add this. This will be what? This will be like a plus b and a plus b. Okay, so here I can take this a plus b out. It is what? 1 into 1. So if you observe, this a is any scalar, b is any scalar. So addition of two scalar is again a new scalar into 1 1. It is still in the format of this, right? It is in the still format of the span of this vector. So it is another linear combination. So therefore what? It also closed. It is also closed under addition. Okay, so all the three properties are satisfied. So therefore the set U, which is the span of this particular vector, is still be a subspace of R2. Okay, so therefore in general if I take U or V, which is span of n vectors, say v1 v2 up to say vn, so this will be a valid subspace of Rn. Okay, so in general, so therefore whenever you have the span of the vectors, it will become a subspace of Rn. All right, so therefore now these are the properties which we are discussing about the subspace. Okay, so now let me just think about another example. Similarly, if you have got the collection of say the functions which can be expressed in the form of the polynomials, say p of x is equal to a naught plus a1x plus a2x up to say an x to the power n. So this collection where a naught even up to an are the real numbers, and your if your p is say p of x and q is say q of x and k is any real number, then if your p plus q of x is defined as p of x plus q of x, and your scalar multiplication kp of x is defined as k times of p of x. If this is how it is defined, then actually this w, the set of all collection of polynomials, will become the subspace of Rn, because we are going to have, if suppose all these even a naught even up to an will become 0, then we have a 0 polynomial which will act as a 0 vector. And after taking any two polynomials, still the addition of the two polynomial will be a new polynomial itself. So therefore it will be closed under the addition. And when you're multiplying with the scalar multiplication to a given polynomial, you'll be getting the resultant new polynomial which is still belongs to the collection W. So hence it obeys all the three properties. So we can say that P of X will form a subspace. Okay, that is very important in order to understand this subspace. I think this is all in the subspace. So let us understand the next concepts in the next video. Till then, take care guys.